Hey guys, so today we are going to do another coding tutorial. So previously what we did was we did a eager mode coding tutorial on a ResNet. We took a ResNet, we quantized it entirely from scratch. Today we're going to be doing FX quantization also on a ResNet. But, and so for those of you who don't know, there's three kind of quantization frameworks in PyTorch. There's eager mode, which is the oldest one, it's the legacy one, it's the one we just did a coding tutorial on. But then there's FX mode and export mode. And FX mode and export mode, they're very similar. They both work on the graph, and they're kind of fundamentally different to eager mode, but they are much better. You should use FX mode, you should use export mode. And so in this tutorial, we're going to be going over FX mode. And the reason that they're better and the reason that they're different is that they're very much part of the Torch 2.0 ecosystem, where we kind of work on the computational graph directly. And that's going to allow us to do a lot of things for free in quantization that we struggle to do in eager mode. Like in eager mode, we had to manually place the quant stubs, float functionals, we had to fuse things manually. In FX mode, easy. It's all done for us. It's amazing. But there are some things then that you have to do in FX mode that you, like you basically still have to do work, right? Like, and this video is going to be split up into a few different pieces. The last piece is going to be doing some advanced graph manipulation, where we're basically going to be going deep in the graph and we're going to be doing some manipulation. So that's something new that we need to learn to do when we're working on the graph. But we'll come to that in a future video, which will be kind of part of this video. It'll be like a part 3. But anyway, yeah, let's dive into the coding tutorial. We're going to take the ResNet model again, ResNet 18 again, completely from scratch, and we're going to quantize it with FX mode quantization. So let's get into it. So to begin with, if you saw my previous video, you will already know what this is, but this handsome little man is a Samoyed dog. And what we're going to be doing today, because we're going to be analyzing ResNet, in order to evaluate the ResNet and make sure everything is working well, we have this little evaluate folder where we have this image that we're going to be feeding through the model. We have our evaluate function, which is mainly taken from the internet, and I will show it now, actually. And so yeah, here we have the online tutorial for the ResNet, and as we can see, it's useful, and it's going to be the basis of our evaluate function. So, you know, they load in the model, and then they literally just get this picture of a dog, they feed it through, and yeah, so we're going to take all of this, and we're going to pop it into our code. And so that was all taken and just put inside of this evaluate function. I added a little bit of code that you can specify if you want to run it on CPU or CUDA, if you do have an NVIDIA GPU available. And it's just going to do all of our classification, and then it's going to output the top 5 classes that it believes the image is, along with their probabilities. And then ImageNet classes is just a text file full of all of the different classes, like RockPython, Green Mamba, etc. And then something else that we have here that is interesting is this IPBD sys accept hook. This is just some code I found online once, and I love it. Basically what this is that if you import this into your script and you run it, what it'll do that whenever you have an exception, whenever you have an error, it'll throw you into an IPDB breakpoint at the location of the error, which personally I love. I find it to be super useful, so we'll see this in use. And then we have our ResNet Pi model. I'm actually going to delete this because, like I said, we're doing this from scratch entirely. So let's get into it. I'm first going to create a main, and then I'm going to create a models resnet.py. What do you mean? Okay, so we have this ResNet, and then what we're going to do is that we are going to go to the online ResNet file, and we're just going to copy paste it and have it here. Yeah, so here we have this ResNet model definition. It's in torchvision models ResNet. And we're literally just going to copy paste this entire thing. And we are going to paste it here. Now, we're going to delete a bunch of stuff from this. So here, because we literally just copied the file and there's all of these relative imports, we're going to have to switch this up a little bit. Cool, so I just replaced all of those, and now it makes all of the imports relative to torchvision, which is what we want. And then Today we're only going to be working with ResNet 18, so we can delete everything else basically. But there is one thing that we have to do. We have to delete this API because this is going to register model, and that's not something that we want to do. And then from here onwards, we can basically just delete all of this. Yeah, I think that's everything that's not the ResNet 18. Then that should be that. So we have, if we go all the way to the top, we have, you know, our normal convolutions that are defined, our basic blocks which are going to be used inside of ResNet, our bottleneck classes, our ResNet class, which is just generally going to be used for everything. Then we have our ResNet 18 weights, which is what we want. Ooh, these 34 weights, we don't need those. So we can delete all of these. And then finally our ResNet 18 model, which is basically a wrapper around the ResNet model, and it's just going to load in the weights if we so wish. So if we go to our main function, we can now import from model ResNet, I can write import ResNet 18. And while we're at it, we're going to import all of this other stuff as well. So from IPD hook, import sys accept hook, and from evaluate, import evaluate. Okay, so this is the basics that we need to actually have our floating point ResNet model. So we're going to do ResNet 18, we're going to write pre-trained equals true, and this is going to load in our weights, and then we're literally just going to evaluate this thing. We're going to say floating point model, and we're going to have evaluate model, and I don't have an NVIDIA GPU on my current laptop, so I'm just going to run CPU, and then I'm also going to run this IPVD sys exception hook just because I love it very much, and here I'm literally just putting an error in the code, and that's automatically going to throw me into a breakpoint. Okay, we can see it's loaded in the weights. It's evaluated the model, and it has correctly identified that this image of this handsome little man is in fact a Samoyed. So cool, that's all working correctly. We've loaded in the weights correctly. We're happy. Now comes the moment that we do quantization. So to do this, we're going to import a bunch of things. So to do FX mode quantization, we need to do a few things. Whereas previously in our model to do eager mode quantization, we had to manually place quant stubs, we had to manually place flow functionals, we had to manually fuse all of our modules. That's all going to be taken care of for us in FX mode quantization, which is one reason it's so good. There are still little things that you have to do in FX quantization, like you might need to manually go into the graph and start doing some graph manipulation if you're not happy with how FX mode quantizes your model, but we'll go into all of that later. So what we're going to do is that first we're going to say act learn QConfig. The first thing we actually have to do, so the general steps for FX mode quantization is we'll assign our QConfigs, we'll decide how each layer, what QConfig it should take, and then we're just going to call prepare QAT and then that's going to do the rest of us for us. But yeah, we're going to get into it. Learnable fake quantize, and now I immediately realize that I have forgotten to import something, so I am going to from torch. I'm sick of copying this, writing this out. So we are going to say from torch AO quantization observer import. I think we'll import a histogram observer and we'll import a per channel min max observer. So okay, for our activations we will set observer equals histogram observer. So here with our QConfig, we're literally just we're creating the kind of ingredient list for a quantization module. So for example, if we then set this as equal to the QConfig for our activation, it would have the observer of a histogram observer. And so a lot of this is boilerplate. It's important to understand. So we're going to say quant min is equal to 0, and I'll write this all out and then I'll explain what it all means. Key type equals torch, it is Q unsigned int 8. We will say Q scheme equals torch tensor affine. I think that's correct. and I have to import torch. And then, because this is a learnable fake quantize, we have to initialize the quantization parameters. So I will do that. And then for this, we also have a use grad scaling attribute that we have to set. I will set that true. It's not going to matter in our use case, but I'll set it for true. Okay, so if you've seen my previous video, you have some idea of what these represent. Histogram observer is a type of PTQ observer. It's going to look at when we're feeding data through, it's going to create a histogram on the fly, and then it's going to minimize the mean squared error between the floating point tensor and the quantized tensor by choosing quantization parameters that are going to minimize that mean squared error. So that's what the histogram observer does in terms of PTQ. Then we have quantmin, quantmax. These just represent what are the ranges of like the minimum value and the maximum value on the integer grid when we move down to int 8 space. This tells us that we're using quantized unsigned integers because we are, in this case, we're just doing affine quantization, so strictly positive. So, we have 0 and we have 255, we have no negative values. We're doing per tensor affine quantization. If you don't know what these things are, I highly recommend you watch my video, which I will be linking here. Then the scale and the 0 point are just the quantization parameters, and use grad scaling is just it means that we're going to use grad scaling if and when we do QAT. We won't be doing QAT in this video, but if and when we come to that, I will mention it more. Okay, cool. So this is what we have for our learnable activation. So I'm just going to post this again. And then we're just going to do the same thing for the weights, except we're going to swap some stuff around. So we're not going to use a histogram observer for weights. We are going to use the per channel min-max observer. And we're actually going to have symmetric quantization. So this becomes minus 128. This becomes 127. This becomes signed Q int 8. And this becomes per channel symmetric. And so that should all be gravy. I'm also just going to create a fixed QParams, or not a fixed, but a like non-learnable version of the activation QConfig, just because I think it'll be useful later. So if I do act, this isn't fixed. What should I call this? I'll call this act static QConfig, and this we will use fake quantize. And this will be a bit funny. We are going to put, there's a slightly different API to this, so we're going to feed these in as args, just because the API for learnable fake quantize and fake quantize is slightly different. Cool, and then because these are fake quantize, we don't give it scale and 0 initial points. We don't have grad scaling. And I think that is all going to work. Okay, so we've created a kind of activation specific and weight specific QConfigs. Now we actually have to create a real QConfig object. So I'm going to call this global QConfig, and this will be QConfig activation equals, we'll say, we're actually going to use the act static QConfig. And then for weights, we're not actually going to use our weight QConfig for this. We're going to use something else. We're going to use the standard QConfigs, and I actually think this is just torch quantization. And what are these called? I want the fused, I think this is the one I want. I want the fused per channel weight fake quant. Yeah, I think I want that one. And then for torch FX, it's kind of interesting how we do the QConfig assignment. The way it's done now is via this QConfig mapping object, which is quite interesting. So, and it's interesting how many opinions there are on how QConfig assignment should be done. It's actually something that's like seemingly quite controversial when it comes to vision, because at least as far as I can tell, every single quantization framework has a different way of doing QConfig assignment. I find it very interesting. But yeah, in the case of TorchFX, this is how it's done. You create a QConfig mapping object, and then this has a bunch of methods, such as setGlobal, and we'll see some of the other methods later, which tell us, okay, how we're going to do the QConfig assignment. So in this case, global QConfig or set global does exactly what you imagine it does, is that it sets all of the QConfigs equal to global QConfig, which in this case is our fake quantize with histogram observer, and then just our default for weights. So we're going to see what that does. So let's say fx is equal to prepare QAT fx, and we literally just take our model, we take our QConfig map, which is super easy, and then we have to feed in an example input as well. And the reason we have to feed in an example input is because what fx mode does is that it does a symbolic trace of the model, and to do a symbolic trace you just have to feed in inputs. Like, that's just how it works, really. So, but fortunately it doesn't matter what input we feed in, so we can just feed in a random image tensor. In this case we're going to feed in a free channel 256 by 256 image tensor, and then we are going to evaluate this thing. And fx quantize the model. I'm going to then take a look at this and we're going to see how it does. Okay, very cool. Our quantize model actually did quite well. We can see it's a tiny drop in performance. Like, instead of, predicting the Samoyed with a certainty of 88.5%, it's 87.8%. So it's not as certain that it's a Samoyed as it was before. But really the most interesting thing about this fx model is when we look at it. Oh, actually, I'm going to put this quote-unquote breakpoint before we evaluate it, because that evaluation is also doing PTQ, which means it's filling up all of these observers with all this data, which is it just makes looking at the state date kind of more difficult than it needs to be. So we're actually going to look at the state date before we do PTQ, because this evaluate is actually doubling up as a PTQ step, because our observers are enabled by default. Oh, here we go. Cool. So if we look at our fx model, it's going to look kind of different to our normal model. So our normal floating point model, which if you use the PyTorch, you're kind of used to seeing this kind of thing, where, in this case, okay, we have a ResNet, we have a conv, batch norm, prelude, we have a max pool layer, we have a layer 1, which is a sequential around 2 basic blocks. Yeah, this all looks kind of conventionally normal, but here when we print out the fx model, we get all of this random stuff. And so just reading the fx model by itself isn't actually the easiest thing to do, and I wouldn't recommend it, but there are some pretty cool things that we can do. Now, because the fx model is literally a graph module, and so this is actually a graph, and so we can do a bunch of really cool stuff. Like, we can use this graph print modular method, print tabular method, and this is going to tell us basically what the graph looks like. This is what the graph is, right? So we take in, at the beginning, these placeholder nodes refer to inputs. Call module, call function, these are all, steps in the graph, and then the output is what is outputted by the graph. So those are like the three main things that you need. You have your place modules, you have everything in between, then you have your outputs. In this case, our input is x, and what this does is basically it's fed in, so just it just reads the x, and then it's fed in to this activation post process, which is going to output an intermediate variable, which is also called activation post process 0, which in turn is fed into the next layer, which is this conv1. And so this is the module that's actually getting called, but it produces an intermediary tensor with the same name. So it's good to understand that this is what's getting executed, this is the output, this is the intermediary tensor, and this is what's getting fed into the next layer. So it's good to understand that that's the case, because sometimes these might be named differently. But these activation post-process steps, what do they represent? Because they weren't in the original module, well, these are our requantization steps. So this activation post-process is actually our initial quant stub. As soon as we enter the model, you need to quantize the first incoming tensor before you do quantized operations on it. That's what this is. This is the first quantization step. Then we have a requantization step after the conv1. We have a max pool requantization step. Requantization steps where appropriate. But I actually want to show you something really cool as well, because already this is great, right? Like this is super nice. But if we look at the fx conv1, we can see that it already did the fusing for us, that we didn't have to explicitly fuse the conv batch norm relu that we had in the original model. where in the original model, if we call conv1 and then it had, I'm actually just going to print out this entire thing because nothing is fused. So yeah, we had a conv1, a batchnorm1, and a relu. These all get fused into the conv1 in this FX model. So it's amazing because if you don't know about fusing, again, I recommend, this next video, which is being linked currently. But the reason we need to do fusing is fundamentally because it comes with massive improvements in performance, in terms of speed. It's just something we need to do when we quantize things, because otherwise we're doing extra re-quantization steps we don't need to do, and we're wasting time, and we're introducing quantization error. But this is very cool, and this conf batch norm relu to the lead layer, it does have a batch norm component, which is updating the statistics as we go. So the batch norm statistics have not been fused into the conf layer. This is currently also updating the batch norm layer with the statistics. If you want to fuse the batch norm into the convolution layer, that's what we're going to be doing next video, and we're going to go more deeply into like graph manipulation and how to do those kinds of things. But for now, we're just going to live with the fact that there's a conf batch norm relu 2D. Okay, very cool. And so really that is the fundamentals of FX mode. Yeah, so I am actually going to call this video here because just to keep it short and to keep it modular. In the next video, we'll be diving a bit more into graph-based quantization and kind of like getting a familiarity with, okay, how is quantization going to work on this graph module basis, on this graph module object. And then in the third part of this video, like we'll call it part C or something, we're going to do some more advanced graph manipulation stuff. Where we're going to be like swapping out modules, where we're going to be traversing the graph, and all sorts of cool stuff like that. So you can kind of gain some more comfort with the graph module, because when you first start working with it, at least for me, I was kind of like, how does this thing work? But yeah, I'm going to call this video here. I hope you enjoyed it. Leave a comment, subscribe, and yeah, I hope you have a nice day or evening or wherever you are, and see you.